All right. So we did a video a little bit about everything. So we'll try to pass over those 250 slide, and just give a few words on each of them, not entering into the details in order to see if we understand a little bit. It will like be the we'll try to follow this red line of the course. So we begin with the hydrostatic equilibrium. We noticed that there was a net force applying upward in order to counteract the effect of gravity. So we explained it, we derived that equality, and when including the ideas gas law, and to it, when we assumed an infinitesimal variation, we saw appearing an interesting quantity that have an importance nearly from the beginning to the end of the course, which is the scale height. The height needed in order to see a pressure drop of a factor E, which means a 60% drop. So we linked the pressure profile to the altitude, and we see that the pressure is decreasing with height. Sorry. Um, so this is the pressure altitude relation, and this scale height, there are some details into it, especially the temperature. So we had to assume some different temperature profiles. This is constant temperature that induced that the scale height was constant. It was the most easy case, the isothermal one, and we ended up with the barometric formula. The pressure is dropping exponentially with the altitude. The density is following the same law. So now we can assume a linear variation of temperature with C. So this is mm, already more correct because the temperature profile, we'll see it later. It's very um, it's very not constant in the atmosphere. So it is already a better approximation of the temperature. So the calculation, the integration of this differential equation was a little bit more difficult. Some change of variables were needed, and some exponential law formulas, etc. And at the end, we ended up with that power law. So the pressure is still dropping exponentially with the altitude. However, it depends now on the coefficient alpha. What just happened? Um, on the coefficient alpha, the density of the atmosphere follow the same law. So it is an interesting result when the temperature varies linearly. So this is exactly the same slide. So we talked about the geopotential height. Like we all know that the potential energy is described that phi is equal to mgh. However, the gravity is changing with the altitude. The gravity is changing with the latitude too. So we can introduce a higher level of accuracy by introducing the variation of g with the altitude. We know. So, for example, here at 100 kilometers, we saw that the gravity was approximately 9.51 meter per second square, which is already a good percentage of the radius of the Earth. And so we define the geopotential height as the work per unit mass to lift an object against the pull of gravity. So this work will be less at high altitude than at low altitude. So the geopotential height was defined as the ratio of R0 Z divided by R0 plus Z. You notice that if Z is small, so we can approximate the geopotential height of being, it will go towards zero. This term will go towards zero. Okay. Totally another topic here, the composition of the atmosphere linked to the scale height. So what happened? We see that between 0 and 100 kilometers, we were in the atmosphere, and after that, every constituent dropped following its own scale height. Yes, and we will see later in the course that um, other processes were included, such as the photodissociation of the O2, such as the ozone, etc. So it was just to know that the composition of the atmosphere is very variable. We see that at high altitude, we see that those light gases take over those heavy ones. We see that we have a large production of atomic oxygen due to the photodissociation. Um, yeah, uh, we see that in this heterosphere, the density varies a lot with the solar activity because um, when the solar activity is high, the scale height is bigger and the atmosphere inflates literally. So, however, it don't have any importance at a low altitude below um, in the atmosphere because the mixing take over the diffusivity. So it was an important graph. We showed the evolution of the temperature. We see that in the troposphere it followed just an adiabatic cooling, following after by an increase of temperature in the stratosphere due to the ozone formation, and in the mesosphere, sorry, you got those NO and CO2 gases that emit in the infrared. Those emissions reach the thermosphere, leading to a cooling of temperature. However, in the enterosphere, we got a high temperature increase due to due to the release of heat because of the production of those atomic oxygens from the photodissociation of O2, which releases a lot of heat. However, the notion of temperature change here because we see that the density dropped exponentially here to values, very low values. Um, so this is why conduction dominates right now. Radiation here in the mesopause, as explained, those greenhouse gases emits in the infrared, while here the convection dominate below 50 kilometers. Um, Concerning the mean molar mass in the atmosphere, by definition, the composition of the atmosphere, the relative composition of each space size remain constant. So this is where mixing take over diffusivity. However, in the heterosphere, we got a complete switch of process. We got due to the very lower density, each space size will follow a decrease um, in their density following their own scale height. So the heavier gas that compose the atmosphere, the N2 and O2, will drop very faster um, compared to the helium. We see that here uh, the helium part of the atmosphere increases. That's what we have seen in the previous slide. We see that the pressure profile dropped exponentially, while here it dropped a bit less sharply, but it continued to drop very exponentially. It is due to the increase of temperatures that will counteract the effect of the barometric in the barometric formula. Yep. Yeah, we saw here also that in the heterosphere, depending on the activity of the sun, the temperature can switch between 900 and 1800 Kelvin. This is an enormous gap. Afterwards, we talked about the conservation of energy. This is the first law, um, where we assumed after that in the lower part of the atmosphere, we got an adiabatic process that will link the variation of the temperature to the variation of volume. So we saw it later on. So it is based on the first principle of thermodynamics. Okay. What do we see here? We assume an adiabatic transformation, so we equal it to the two members. Um, on the right hand side, we got the variation of the volume that is linked to the variation of temperature. So um, when the gas expands, or when we have a variation of volume that is positive, we got a decrease in temperature. Playing with some formula, assuming an ideal gas, we link the variation of pressure, and knowing the link between the pressure and the altitude, we introduced the scale height, and at the end we um, we were able to notice that in the lower part of the atmosphere, the variation of temperature with respect to the height is constant and negative following this coefficient. So this is explained by this formula here. So this coefficient gamma is G over Cp, and this is what we call the adiabatic lapse rate. So we went from a higher temperature in the lower atmosphere, and when we increase the altitude, we notice a linear decrease in temperature. This adiabatic lapse rate, when we approximate it with the value of the gravity and the Cp, we see that we have 9.8 Kelvin per kilometer. However, what do we observe is a lower value of 6 Kelvin per kilometer. So we got a 40% gap that can be explained by the fact that this variation of volume do not directly impact the temperature of the air, because a part of it, we missed a part of we neglected the water vapor and its change of states. So instead of cooling down the air parcel, it will just take this energy in order to change state of those of the moisture that compose the air. So we can approximate this gamma value by 6 Kelvin per kilometer. So as explained, the rising the air rise, it expands and the temperature is dropping. So we got this inverse relationship between the temperature and the volume. So expanding air, lower density, lower temperature. So in reality, atmosphere is not fully controlled by adiabatic convection. So what can we explain right here is that if we assume that the atmosphere cooled down a bit too fast right here, we went from T1 to T2 prime. And if we assume, for example, air parcels that cool down from 1 to 2, so this one will have a higher temperature, which means a lower density than the atmosphere, so it will just continue to rise. It can be associated to a balloon full of air that will just continue to rise because the density is lower. So this is what we have, a reinforcement of convection that will make this adiabatic curve to come and follow that will increase T2 prime to T2. So we are going to the adiabatic case back. So in this case, we say that the atmospheric distribution is convectively unstable. On the other way around, we can do exactly the same. For example, you got the atmosphere that go from 2 prime to T1. So the atmosphere would have a temperature which is higher, so it will have a lower density. And if you assume a air particle which is going from 2 prime to this temperature, which is lower than the atmosphere one, it means that the density is higher, and it will just be associated. You can imagine the analogy is the one of a rock that is falling inside the water, so it will just also reinforce convection. So this particle will just continue to drop. Um, Okay, now we can have another case when the atmosphere cool down to a temperature which is higher than the adiabatic one. It means that the density is lower, and is the density is lower than a particle that cooled down adiabatically. So here the density is higher than the atmosphere, so it will not continue to rise and it will be stuck. So the convection is inhibited. The atmospheric distribution is convectively stable. You can have those extreme cases that happen. We call it the thermal inversion that can lead to smog. This is when the temperature is increasing with the altitude. So we got extreme convection inhibition. So we can switch to another topic right here, which is the radiative equilibrium, where we did some hypothesis. The atmosphere is transparent to the solar radiation, and the top atmosphere fully reaches the ground. So remember the curve in form of a bell of the sun, which emits mostly in the visible range. So we can assume that it is mainly correct. So 40% of the emission of the sun is in the visible range. So the atmosphere, the second assumption was the individual parallel layers. So we completely neglect the fact that the Earth is spherical. So we assume that it interacts with adjacent layer. Only we assume that the atmosphere is in radiative equilibrium, no source of energy in the atmosphere. So this simple model can be, we can draw something right here. So there are parallel layers, 1 to n, radiating energy toward the adjacent layer, nothing more, nothing less. Black body, there will be two black bodies, so the emissivity is equal to 1. Solar radiation, absorptivity 2. Solar radiation enters the atmosphere in layer 1. Okay, layer n receives the infrared radiation emitted by the ground towards the atmosphere. So the radiative equilibrium energy flux from the sun is equal to the one emitted by the Earth. So what do we emit? Sigma T1 to the power 4, and what do we receive? The sunlight. So F is the sun energy. Sigma T1 to the power 4 is what we emit to Earth, and sigma T1 to the power 4 is what is emitted from the Earth. So sigma T1 to the power 4 is exactly the same as sigma T. No, it's not the same. Yes, this is the sorry. So T1 is the emissive temperature of the Earth. So what is entering is what is going out. Yep. TE is the effective temperature in the Earth's atmosphere. T1 temperature of the outer layer corresponds to the infrared radiation emitted to space. So in each layer we can do this equilibrium. So in the first layer, what is emitted? 2 sigma T1 to the power 4 upwards and downwards, and what is received? Only sigma T2 to the power 4. We can do it for each layer. What is emitted by layer 2? 2 sigma T2 to the power 4. What is received? T1 to the power 4 and T3 to the power 4. We can do it for each layer, blah, blah, blah. And at the end, we can do it at the ground. So what is received? What is emitted? Sigma Te to the power 4, temperature of the Earth. What is received from the to the ground? Sigma Tn to the power 4, plus the sun contribution. N plus 1 equation, N plus 1 unknown, it can be solved. The temperature T1 is equal to the emissive temperature of the Earth. T2, T2 is T2 to the power 4 is 2 times T1 to the power 4, so there is a factor. So we cannot say that T2 is 2 times T1. It's not true because there is this force power here. No matters. So T2 is the square. Wow, is 2 times to the power minus 4 greater than T1. So there is not an increasable rise in temperature. However, you can see that it is growing following this power law. And at the end, you got the temperature of the Earth, which is equal to N to T1 to the power 4 plus the contribution of the sun. So was the second hypothesis right? In reality, if the layers are too thin, we can have interaction with two or more. If they are too thick, we can have self-absorbed radiation. So this is a problem. All right. Additional layer of temperature T0. Sorry, I'm just need to write something. Okay. So we add a layer that now have some characteristics such as the absorptivity and the emissivity, opacity, sorry, and emissivity epsilon. Radiative budget, what is entering sigma T1 to the power 4, what is going out, 1 minus kappa. sigma T1 to the power 4. And what is going out is epsilon 2 sigma T0 to the power 4. We can assume that epsilon is equal to K, to kappa. Right. So this case, classical radiative equilibrium right here, that end up to the definition of the skin temperature, which is T0. This is the temperature reached at the top of the atmosphere. T0 is the half of T1. Uh, this is a bit accurate because the temperature is close to that of the tropopause. So this model applies satisfactorily to the Earth's troposphere, so the very first part of the atmosphere. In the outer layer, we got ozone, O2, etc. So we cannot continue with that model. So this is about sun emission now. The sun emits 4 pi radius of the sun, sigma Te to the power 4, assuming that the sun is a black body. And what is received by the sphere, the whole universe, I would say, not universe, but all the solar system, sorry, is 4 pi a squared to the power s. This is the power received when we are at a radius of a, which is an astronomical unit. So the Earth is at 1 astronomical unit from the Sun, which is 150,000 of million kilometers. No, 150 million kilometers. Sorry. So we can approximate then the sun emission, and this is approximately this value. Yes, it varies depending on solar activity, the sunspot, the Earth, and distance, because of the elliptic orbits of the Earth around the sun. Yep. So we assume that the sun behaves like a black body. This is more or less correct. We'll see it later on. Black body spectral radiance distribution follow the Planck's law. So the sun emits following the Planck's law. We'll see it later on also. This was derived by Planck and led to the UV catastrophe, and this is the birth of quantum mechanics, etc. So this law is quite accurate for the sun. So it depends on temperature, etc. On temperature and obviously on the wavelength. The winds displacement law provide us the wavelengths at which the sun emits the most. So the sun is approximately here. It emits mainly in the visible range is between 400 and 700 nanometers. Here it's in micrometers. So yeah, this is the black body radiation following the Planck's law. So the sun here in yellow emits mainly in the visible, as you can see. So yes, so the black body assumption is more or less correct in the visible and the infrared. However, you can see that the sun in the UV range is subject to higher variation first, but then don't follow this black body law. So how is the sunlight absorbed at the top of the atmosphere? This is what we have, and at the surface we see that the grid part here in the UV is dampened. Fortunately for us, a grid part of the sun emission is actually absorbed mainly here in the infrared, thanks to the greenhouse effect. We see that in those wavelengths we got a great absorption, especially by the water, CO2, etc. So in the what is interesting with the ocean is that it absorbs everything in the red that comes from the surface. Everything in the red part is absorbed from the ocean, um, except for the blue parts. This is why ocean is blue. So now at the top of the atmosphere, blah 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 again. So we got absorption bands, CO2 issue, etc. Right, there are greenhouse gases. They absorb sunlight, so this is why we don't want them. Variability of solar emission. Yes, we talked about the variability because so we got the sun emits mainly in the visible. Fortunately for us, so this is a logarithmic scale. You see that it emits way less in the UV, and fortunately for us, because the UV range is the one subject to the more variability. Just imagine if you had a high variability of the sun, In the visible range, we would have one day minus 40 degrees, the other 40 degrees, etc. Now, we have a very low variability in the visible range. So this is the solar cycle variation due to, yes, we talked about the cycle of, yes, the sun cycle, like how the magnetic field of the sun is varying from being a poloidal to a toroidal, etc. So it affects the solar irradiance, and this is a well-known pattern. Fortunately for us, it represents less than 0.07%. Um, so the sun variability has effect. So in the very high atmosphere, so in the heterosphere, thermosphere, we see that the photodissociation of molecular oxygen liberate heating and highly depends on the photons of the UV photons, the most energetic ones. We see that when the temperature is increasing, no, when we have a high solar activity, the temperature can increase a lot, can nearly double it from 700 to 1400. We see also that the scale height of each space size will increase with the temperature, leading to a higher density of the atmosphere. The atmosphere will just inflate, leading to a higher density here. We go from this to this, so nearly 100 times, uh, even 1,000 times denser, which leads to problematic stuff, especially for the low Earth orbit satellites that will now be affected by drag, that will have a higher drag. Um, so here we talk about the diffusive equilibrium. So this is the scale high. We are at thermosphere, heterosphere, so each component follow its own scale height. Your hydrodynamic breaking of Leo, yes, the what do we see right here? Satellites may become an issue with, oh yeah, at low Earth orbit when the solar activity is high, we have a breaking of satellites. All right. So now we talk about general form of the radiative transfer equation. It explains the photon number of the photon number in a given direction, the radiation in a given direction. How does it vary? So it is altered by atmospheric gas elements. So you can imagine that the attenuation, the intensification will not be the same depending on where we are in the atmosphere. So the variation of this intensity of radiation, variation of the radiance, will vary depending on those two quantities. You got emissions, so it relates to a positive value of the variation when we have got an emission of photons. If we have absorption or scattering of this photon, it will lead to a negative variation. So call it so this is losses, this is gains. So this is a schematical view. We can have gains from the scattering of other photons in another gas element, so it can be quoted positively. We got a loss due to scattering coefficient sigma. We can have loss due to absorption. Yes, the absorption coefficient, and we'll see that the absorption will dominate in the infrared range, and we have seen that the scattering dominate in the um, short wavelengths range, and we can have a gain due to emission or inelastic scattering. Summary. So we introduced the source function by multiplying both sides by this coefficient, and here we defined the optical depths. Okay, optical depths. The higher the optical depth will be, the higher the difficulty for photons to go into towards the end of the gas elements. So the more you have probability to be absorbed. So we got the canonical form of the radiative transfer equation. So, all right, it can be rewritten. So this is exactly the same slide. They are double again. Sorry. Um, so first case, you got the pure attenuation. You got no emission. So source function is equal to 0. And if you integrate that, you note that the intensity of the radiation will drop exponentially following the optical depth, which is the sum of the absorption and scattering coefficient. So we got an exponential law of attenuation. So yes, when we got pure scattering, this is the case of the atmosphere under clear sky condition in the visible domain. So visible domain is dominated by scattering, don't have a lot of absorption in the range. So I assume that the kappa nu, the absorption coefficient is equal to zero, and we assume that um, the source function is then different from zero because you can have scattering from other gas elements. So light transmitted results absorption, but with diffusion. The scattering is characterized by this phase function. So probability to a photon with initial direction to be scattered in another direction. Uh, this is a complex integral that needs to be normalized. So the source function is the following one. So integrating between in every direction in both hemispheres. So this is the source function integral. So what is gamma omega? Sorry, I don't know. I don't know from where this comes as a formula. So I need to write it. I think it's not important just in order to explain from where this comes is 1/4 pi coefficient. So no matters. What is the local thermodynamic equilibrium and where can it be applied? We say that the local thermodynamic equilibrium is the intensive parameters like T, N, or P are varying space and time, but are varying so slowly that at any point what can be assumed thermodynamic equilibrium in some neighborhood about that point. Uh, okay. It is the case only in a part of the spectral range, which is the infrared one. The medium is in equilibrium with solar radiation, and both are completely described by the temperature. Okay, so this is the local thermodynamic equilibrium is applicable only in the infrared range. So first 60 kilometers of the Earth are a result of the many absorption and re-emission in the air by the dense atmosphere. So if we increase the altitude, we are in the mesosphere, and we don't have uh, many absorption and re-emission. So this is a threshold up to this altitude. We don't have the local thermodynamic equilibrium that can be applied because of the lower density. LTE applies if population are dominant, and if the gradient of temperature is small enough. So what does it mean collisions are dominant? So we got a high absorption coefficient that is high, and a scale height that is way higher than the mean free path of the photons. Does it apply in the upper atmosphere where absorption is too scarce to reach equilibrium, decoupling between kinetic temperature and radiation temperature? So yes, when we increase when the atmospheric density is very low, you got a mean free path which is way higher. So the scale height, the mean free path of the photon can be a significant percentage of the scale height. This is not applicable again. So local thermodynamic equilibrium, we got some definitions right here. We can assume that the emission coefficient follows the blackbody radiation. So this is LTE, and with emissivity that varies with the wavelengths. Under LTE, Kirchhoff's law is applied. Absorptivity is equal to the emission, so the source function can be simplified. And so we can assume that the scattering is very low because we are working with higher wavelengths in the infrared range. So S nu is equal to B nu to the power B nu depending on the temperature. So we can combine it with the canonical expression of the radiative transfer equation, and when replacing it, it leads to the Schwarzschild equation valid in the infrared domain. So this is a visual view of the balance between the incidence, reflected, transmitted, and absorbed radiation. So we got Fi that leads to Ft plus Fa plus Fr. It needs to be equal to 1. So note that when the albedo is equal to 0, the opacity is equal to the absorptivity. So we got the evolution of the the radiation inside the gas element that will drop exponentially with the optical depth, the difficulty to reach the end of this gas element, and plus the source for what is contribute to this radiation. So we got some source function depending on where we are in the atmosphere. We have source function in the visible range, for example, that would be mainly scattering, and we got a source function in the infrared range that will be mainly the black body radiation. So if we plot on the same graph the black body radiation of the sun and the one of the Earth, so on the left part you got the sun, on the right part you got the Earth. So and we can we have a limit here. If you assume, we would assume that one lambda is lower than 4 micrometers, it is the sun that will dominate. While in the other case, we got the thermal infrared of the Earth that will dominate. So the absorption spectrum in the atmosphere, what do we have right here? We see that in the UV range, you got a very high absorption thanks to the ozone and the molecular excision. In the visible range, you have nearly no absorption, while you see some significant bands begins to appear in the near infrared and infrared, where the sun emission begins to be a bit lower. In the infrared, where the Earth emits, we see that we have a lot of absorption, mainly due to those greenhouse gases. Remember that the local thermodynamic equilibrium is applicable here on the part uh, of the emission range of the Earth. So this is mainly what we just explained. So in the UV domain, we got the black body emission, which is approximately equal to zero. So the variation of the intensity of light is equal to the initial one, to which we will decrease. We will have some scattering, and we will have some attenuation due to the absorption. Uh, we got an attenuation proportional to the optical depth that will mainly be here in absorption coefficient. So, all right. In blue, you got the scattered part, integration over incoming direction leading to final direction, and you got the phase function also. So, all right. Uh, no emission of solar radiation in the atmosphere. Yep, that's right. And got this coefficient beta, the sleep at beta, that is defined as sigma nu over sigma nu plus kappa nu. So when you don't have any scattering, you got zero approximately with this coefficient. So this is a reminder of what we just explained before in the video. Um, so all right. Uh, So this is a schematic view. So you got the sun emission. Is it absorbed? Yes. So it will be categorized as absorbed photon. If it is it scattered? If it is yes, it will be categorized by scattered photons. And again, do the scattered photons are absorbed? If it is the case, okay, absorbed photon. If it is not, you got scattering. If they are not scattered, then they continue their life, and so it will continue downwards, etc., eventually reaching the ground. So in the visible domain, we don't have attenuation term anymore, and we just have this scattered part. Again, depending on this phase function, taking into account the probability of emitting from a direction and reaching another one. So integrating over 0 to pi and -1 to +1, so it is over the whole domain. So the variation of the light radiance is actually the initial one minus the scattered part. So in the near infrared domain, what is happening right here? We begin to have strong absorption band, and we have some attenuation. The attenuation terms come back right here. We'll have some scattering. Scattering is less and less efficient because the wavelengths are actually more and more higher, bigger. So that's what we got in the fine infrared domain. We got the blackbody emission it is taking into account. So now this is mainly the Earth that emits temperature, and we got that upward flux. And then we go back to the Schwarzschild equation, where the local thermodynamic equilibrium is applicable. So the source function is equal to the blackbody emission function between 0 and 60 kilometers. We stop it at the mesosphere because the assumption is not valid anymore. The density is too low. The mean free path of the electrons of the mean free path of the photons begins to be comparable to their scale height, so the local thermodynamic equilibrium is not applicable. Application to the Earth's radiation, we assume a gray atmosphere applies to a gas that does not have the properties of a black body, but whose absorption coefficient is independent from the frequency. We assume that the absorption coefficient is constant on a range, and we'll say later on what is interesting for us. So in the first part of the range, like we have an absorption coefficient which is approximately equal to zero in the visible, while we assume that we have absorption bands in the infrared, and we assume this absorption coefficient to be greater than zero. So we can associate the atmosphere to the glass. We see that in the visible range, when we don't have any absorption, we can see the eyes of the man right here. While in the infrared domain, the absorption begins to be bigger, and we are not the light is not able to reach the eyes of this man, so we are not able to see his eyes. So how did we approximate this absorption coefficient? We did an integral in order to take into account the weight of the blackbody radiation into it. Let's assume that the atmosphere is horizontally stratified. So this is a plane parallel approximation right here. The gray atmosphere heated from below. We got some simplification again. Energy is transmitted through radiation only. We assume no conduction, no convection, no scattering. So right here, so assuming that the radiative equilibrium was reached, which means that the scattering coefficient was equal to zero. So the optical depth was just now the minus kappa nu rho dz. So we go back to the Schwarzschild equation. Integrating over all the frequencies, this is what we got. If we add some other simplification, assuming that LT is the bulk of the energy is transported by thermal radiation in the far infrared, this is quite a decent approximation. So, assuming that the optical depth doesn't depend on the frequency because we have approximated by the Russell mean. So this is equal to E minus B, B being the blackbody radiation. The Schwarzschild equation allows us to find the evolution of the intensity of the photons with respect to the optical depth, leading to the that can lead us to the temperature variation with the optical depth. But how this optical depth varies with the atmosphere, and how the temperature vary finally with the altitude. Sorry. So if you go back to that Schwarzschild equation in the valid in the infrared range, multiplying it by 2 pi and integrating, this is what we call the first moment of an equation. This is something that we do usually. So we have the unit of a flux right now because we multiplied it by mu, which is the variable of integration. So we multiplied it by mu here, and so on the right hand side you see what we call the mean radiance, 4 pi the mean radiance appearing, and here you still have the blackbody emission B. Okay, that does not depend on the orientation. So finally, if we are written that the variation of the flux with respect to the optical depth is equal to this. We assuming that the flux is constant. we don't have any source, don't have any loss, no convection, no conduction. The radiation is constant, leading to this radioactive equilibrium. The radiance is equal to the black body emission. All right. So we can integrate again here, but by multiplying by 2 pi mu. This is the second moment that we take right here, and we see this has the unit of a pressure. The variation of pressure with the optical depth is equal to the flux. However, we need, in order to be able to find the intensity of the radiation with respect to the optical depth, we need to introduce a two-stream approximation. We'll talk about it later on. So there are the expression of the mean radiance, the indicator flux, the K integral, which is linked to the radiation pressure. Two-stream approximation. So the emission is going. There are two choices for each photon, upwards or downwards hemisphere, E plus or E minus. So independence of theta and phi. This very simplified the radiation, the flux, and the radiative pressure. So they are simple. For the flux and the radiation, it is very simple. For this integral k, we can solve it without any problem, and it leads us finally to the variation of the mean radiance with respect to the optical depth, which is linked to the flux. Assuming that the flux is constant, so we see the evolution of the radiance with respect to the optical depth, which is linked to the flux. What is the initial mean radiance? The mean radiance being the mean of E plus and E minus, yes. So G0 is 1/2 E0 plus, simple as that. Yep. So we can introduce it in the expression in order to find the initial flux. That is 2 pi I0 plus divided by 2, which is pi 0 I0 plus, which is constant. So the initial flux is the final flux too. So we find that the mean radiance is I divided by 2 pi. So we replace here, and it simplified the expression like this. So this is what we got right here. And knowing that the radiance is equal to the blackbody emission, so it can we simplified it, and we got the blackbody emissions that depends on temperature. So later on we'll be able to find the temperature. So you introduce the flux with respect to the blackbody emission, and you got finally, knowing that B is equal to sigma T4 to the power pi to the power 4 divided by pi, we got the evolution of the temperature with respect to optical depth. This is what we were looking for. It is increasing with optical depth. This is what we call the greenhouse effect. Heating results from the combination of transparency of the atmosphere to visible light and the strong opacity to infrared, where Planck's function is maximizes. Just remember the expression of the optical depth, combination of the absorption coefficient and the scattering one. All right. Super. We can now derive the effective temperature. So if we assume, yes, we know that the temperature, the skin temperature T0 is equal to T0 to the power 4 is equal to Te to the power 4 divided by 2. All right. And so it allows us to find the effective temperature, which is the temperature when 2 is equal to 2 over 3. So we found out the effective, we found out the optical depth of the effective temperature. So what is the temperature with respect to the altitude right now? We can, in order to do so, first we need to do a global radiative budget. So the received power to the Earth is PR to the power E, PR squared to the E, Fs 1 minus A. Fs is the sun emission in watt per square meter. And as the Earth only have p r squared to the power e as a surface that see the sun, while the sun emits in on the spherical surface 4 pi r square e. So at the end of the day, it allows us to find the effective temperature of the Earth, which is also the temperature of the ground if we had no atmosphere. This is the temperature at the top of the atmosphere, like without any atmospheric effects on it. So we need to find the evolution of tau, the optical depth, with the altitude. So most probably it will grow with the optical depth is decreasing with the altitude. Sorry, so the optical depth is the difficulty to reach. Oh, so the higher the optical depth, the higher the absorption will be. So we see that the optical depth will probably increasing the closer we are to the ground. So yes, so in order to approximate tau z, yes, we go back to the Russell-Lambda approximation. So this is the definition of the optical depth. Yes, we replace rho by its definition depending on the absorption cross section, and as uh, the gas that is absorbing the most is actually the vapor water, so we can replace the absorption section by the one of the water, and the density by the one of the water too. Um, However, the density is decreasing with the scale height of the water with altitude. Knowing the scale height of the water being 2 kilometers, we have everything needed in order to integrate and find finally the evolution of the optical depth with the altitude. So when z is equal to infinity, the optical depth is going to zero. Why? It is because we don't have any absorption anymore. Right? So this is a boundary condition that we have. When z is going close to zero, the optical depth will be the one of the ground. So finally, we find that the tau sigma h to 0 and 0 is equal to the optical depth difficulty. The optical depth is the difficulty to a radiation to pass through a gas element. So tau z is equal to tau j exponential, decreasing exponential with the altitude, as expected. So we find finally the profile of temperature, how this temperature is evolving. Tz to the power 4 is equal to Te to the power 4 divided by 2, 1 plus 3 over 2, tau j exponential minus z over 2. When tau j is equal to 1.5 and z is equal to 0, we can find the temperature of the ground, which is approximately 288. Right. So this is the temperature profile that we got at the end. We got a temperature discontinuity, however, because we only assumed the radiation. So we see a very great gap between the ground, between the surface, and between the layer of air directly above the surface. We see a 30 degrees gap. It is because we only assumed radiation as heat transport. It can be associated as the kitchen heater right here. If you if your hand is a little bit not too close to this heater, you will just feel a little bit of heat. However, if you touch it, you will be burned directly. So this is the gap right here. This is because it emits mainly in the radiative domain. It is a radiation process. However, in her case, this infinite gradient of temperature is due to the fact that we did not include the convection in her explanation, and it can be explained by the following slide. So it just shows that there was a temperature discontinuity due to only assuming a radiation exchange of heat. So the ground temperature is very different from the air temperature just above it. So it can be explained through the true stream approximation and the radiative equilibrium, we see that here we assume that the temperature at the top of the atmosphere was equal to zero. However, when doing this small development, it leads us to temperature at the top of the atmosphere, the skin temperature, which is different from zero. Using the same development, assuming the mean radiance and the flux being equal, so you got A plus and E minus equal to this, and assuming that the mean radiance of the surface being equal to the mean radiance of the ground. So ground radiance is equal to radiance of the area in contact with the ground. So we got a radiative equilibrium. So concerning the surface, we don't have any flux passing through it. So it's only blackbody emission of the temperature of the surface. However, for the ground, we got a flux that is passing through it. So in order to compensate for the missing flux, the temperature of the surface needs to be higher than the one of the ground. So this leads to the temperature discontinuity. Sorry. So it can be represented right here. You can see that the ground black body emission plus the F over 2 pi leads to the black body emission at the temperature of the surface right here. So this is just the missing convection in that radiative model that leads to this gap in temperature. So we have a superadiabatics in blue leading to thermal convection. Right here, when you're only assuming the radiative model, we got a temperature discontinuity convectively unstable. This is cancelled by convection. So convection is here in order to make it to fix that small problem. All right. What will we do? Radiative equilibrium, no convection. I don't know what I need to fix in order to understand what is on that slide. All right. The energy budget and the climate, global radiative equilibrium with an energy balance. So assuming that the incoming energy is the solar radiation through the cross section. So nothing complicated, and we already done this this equilibrium before. Assuming albedo is approximately equal to 0.3. We find the emissive temperature of the Earth being 255 degrees. So we got something called the photosphere, where the Earth is emitting, which is not the ground. Temperature measured by an error detector in outer space pointed at the Earth. So assuming that it is over 4 solar radiation is assumed to be equal to this 100 units. So you got 100 units coming down to the Earth. So you got 28 that directly access to the ground. So but you got 21 that is absorbed through the ozone, the molecular oxygen, etc. The dust. So 21 of the 100 units you got, 30% at the end that is reflected through the albedo, reflected at different stage of the atmosphere. However, the most of the part of the reflected is the upper atmosphere. So you got 24 units that are absorbed, as explained. You got 25 that are scattered thanks to the Earth and the cloud. So those scattering units, 21 of them reaching the ground, while a part of it is directed and are counted with the albedo of the Earth, so 30%. So at the end, got 25 plus 21 units of light of visible light that access to the Earth, so 45. So concerning the Earth, it emits in the infrared. It emits a lot. It emits 113 units, 113 units in the infrared domain, and from those 113 units, 107 are absorbed. Okay. To the 107 absorbed, you can add the ones that were absorbed into visible, 21 plus 3 plus 107 plus 23 plus 6. So you got at the end a lot of that are a lot of units that are emitted absorbed, and we will have a redistribution from those absorbed. There will be a part that will be emitted back to the earth. It will lead to 97 units coming back to the earth and 63 that are emitted towards the atmosphere. At the end, the budget at the top is respected and the budget at the bottom is respected too. So it's an interesting result that we see here, how the units of light, etc., are redistributed, and how the conservation of energy is applied in the atmosphere. Each system receives 100 energy units and emits 113 units. This is a consequence of the greenhouse effect due to the optical depth at the ground. So the temperature of the Earth is the temperature of the ground air plus the one of is the skin temperature. The blackbody infrared radiation from the Earth is larger because temperature of the Earth resulting from absorption of extra infrared downward radiation from atmosphere is larger than without atmosphere. All right, they don't understand very well this slide, however, no matters. Atmospheric photochemistry. We have a lot of stuff to say about that. What is happening? This is mainly applicable in the upper part of the atmosphere when the molecular oxygen will absorb some photons and through it will be photodissociated, or even if the photons are even more energetic, it will lead to ionization. So if we are focusing in the middle UV range between 1800 and 2400, we got what we call the Herzberg continuum that will lead to dissociation of the molecular oxygen into atomic oxygen in their near energy level 3p, the lowest one. This is a continuum, which means the upper level are not quantized and form a continuum. This will lead to a continuum line, the continuum of Herzberg right here. What is interesting here is that the photodissociation will lead to the formation of atomic oxygen. Atomic oxygen that will be a reform that will react with the molecular oxygen, leading to formation of ozone. All right. This is the rate of formation of molecular oxygen. We'll talk about it later on when there is a constant right here. So so we are switching the RO-SPSI into a photodissociate one. Okay. You got the ionization continuum for the UVs that have more energy, which means the lower wavelengths UV. So here you got enough energy in order to photodissociate and ionize this molecular oxygen. Here you got an interesting thing here, where the section of absorption is lower, meaning that the energetic UV are allowed to travel a little bit more inside the atmosphere and leading to the formation of what we call the ionosphere. So the relative importance of the molecular oxygen and the ozone. So we see that for the very energetic photons right here, we both have a high section of absorption for the ozone and the molecular oxygen, leading to an effective damping of those extreme UV. We see that the solar emission range, so the solar emits way more and more as the wavelength is increasing in the UV range, fortunately for us, because and in the parts where the UV are still harmful here, between 200 and 300, this is where the ozone will play a big role in the stratosphere. We see that the section of absorption is increasing right here, leading to an effective damping of those harmful UV. Here we're increasing the level of the wavelengths right here, and we see that we are going more and more into the visible range, and the section of absorption is less and less, allowing the sunlight to access the earth. So the altitude at which those damping of the UV is happening, we see that the more harmful the UV, the earlier it is dumped into the atmosphere. So below this curve, the UV are considered as attenuated, and up here they are considered as. And then when we see that for the visible light, this the altitude of 2 equal to 1 is never reached, which means that the visible light is access to the ground very easily. We see that uh, for in the middle range right here, we see that it is the molecular oxygen that do the job, and for the more energetic one, we see that the photodissociation of molecular oxygen leads to the ionization of the atomic oxygen right here, creating the ionosphere. Here we can see the Lyman window allowing for the UV to access the beginning of the mesopause right here, the mesopause nearly, so leading to ionosphere. Um, yep, we are exponentially attenuated under this curve. So we talked about the importance of ozone. Now we need to know how is this ozone produced. We got those five steps. For the first one, the photodissociation of the molecular oxygen leading to atomic oxygen. The atomic oxygen through the cell body recombination will lead to formation of the molecular oxygen that will react with atomic oxygen remaining, leading with the third body, leading to the formation of ozone that will be destroyed by the same atomic oxygen and by the UV again. So we need to know what is the concentration of the ozone. The variation of the ozone quantity is the difference between the production and the loss. We can assume that we can define the OX family, which is the sum of the concentration of the atomic oxygen and the ozone. We see that in the stratosphere, ozone is dominated over the atomic oxygen, so we can approximate the variation of the odd X family, the OX family being the variation of the ozone only. We see that in the mesosphere, the ozone still dominated over the atomic oxygen. So we can do the two approximation will be useful for us. So in the stratosphere, the lower mesosphere, when the atomic oxygen concentration is lower than the ozone one, we can approximate the OX concentration family being the one of the ozone, which is simplified the expression of the variation of the ozone quantity, which is approximately the one. Uh, we can simplify the expression of the variation of the OX family being the one of the ozone, leading us to, if you assume even more steady state, the variation of ozone is simply given by this formula. However, we need to know the concentration of atomic oxygen. We need to uh, go back again to the variation of the ozone quantity, assuming steady state, leading to we can express the atomic oxygen concentration based on the one of the ozone and the one of the molecular oxygen and the third body recombination one. So at the end of the day, we are able to trace the evolution of the ozone concentration, and we see that it overrates the production of ozone. So we have too much ozone. So we need to include other constituents such as the HOX family, the NOx family, and the CLOX family that will play the role of ozone destruction, and explain why we have destruction of ozone in the Antarctica. We will see that it is intimately linked to the chlor concentration. So this part is important. You see that as we are in the atmosphere, the density is dropping. However, the relative concentration can stay constant. For example, this for all those diagonal lines, it means that we have a constant mixing ratio. This is the case for the CO2. Okay, and however, it is not the case for the ozone. We see that in low altitude, in the stratosphere, the ozone concentration is increasing. However, it drops rapidly right after, starting from the 60 kilometers. We see that we have a high, very destruction of ozone. The concentration of atomic oxygen is rising, as you see, because of the photodissociation that is more efficient on the upper layer on the atmosphere, as we have seen with the penetration depth altitude. Um, so our model was not the Chapman model was not efficient in order to explain the ozone destruction. We see that we have plenty of different speci. The chlor one, for example, here the N1 right here, that will be subject to investigation in order to explain why is the ozone concentration dropping with altitude. So for that, you can introduce, for example, the NO, uh, the NO, yeah, recombination process after formation that will lead to a catalytic cycle. NO, N2O is a natural element that you can find in the atmosphere that will just rise and react with the atomic oxygen, leading to NO formation. NO will participate to a catalytic cycle, which means that it will destroy the ozone while being not destroy itself. So you see that we have to process it react with the ozone, destroying it, leading to molecular oxygen formation, and it will react with the atomic oxygen remaining in order to going back at NO form. And it will explain the loss of ozone concentration, especially in Antarctica. In addition to this catalytic cycle, we got the partitioning of NOx constituent into what we call some reservoir. So the NO2 produced right here can react with can be photodissociated into NO that will react itself with some HO2. HO2 it's just from can be formed, for example, with the reaction. I see with the reaction of the uh, O2 minus and the water, which is a greenhouse gas available in the lower atmosphere. That will lead to the formation of this HO2 that will react with the NO in order to produce some OH plus NO2. OH plus NO2 is a third body. This is a third body recombination process, so we need to have a high density because M will be important is that in that formation, which will lead to nitric acid. What do you see right here? So this nitric acid is the storage of NOx and HOx in a reservoir of HNO3. Those two gases are uh, responsible of the destruction of ozone, as we will see later on. So this reservoir can be reactivated through different processes, especially during the day, and lead to the formation of a second reservoir, which is the N2O5 N2O5 that will lead to the formation of NO2. So NO2 is reactivated. NO2 and NO, by the way. So it explains the formation, the release of those harmful gases that will lead to the destruction of ozone are due to the reactivation of those reservoir, which is the HNO3, which is released in the spring. So it will explain why during the spring the concentration of ozone over Antarctica is dropping. So here catalytic cycle, here with the NO space psi. So yeah, it is a slide that we just passed over. So we cannot determine the concentration of ozone, not immediately because we need to do the photochemical equilibrium. Production minus loss minus transport, we assume that the transport is negligible. So we again pass through it and we express, we need to find the variation of, what is that? Uh, Photochemical equilibrium. Okay. The production is equal to the losses. Production of NO, the loss of NO, so you got NO2 over NO. It is important for us because um, as we have seen or here that the NO is responsible for the destruction of ozone. So production is equal to the losses. Other source of NO, bombardment of N2. Okay, no matters. So we have the Chapman model where we include the NO cycle, catalytic cycle right now. So it will increase the level of accuracy of our model. However, we see that the NO is dropping very rapidly when we increase in the very first part of the stratosphere, in the troposphere. Um, so NO can explain the destruction of ozone on the lower part of the stratosphere, but however, the Uh, on the upper part, we cannot explain it. This is why we need to include the CLOX family and the HOX. So this is the CL family. We explained that it is also responsible for ozone destruction. Those are found in aerosols, etc., refrigerants. So they are also very responsible for ozone destruction. This is why we need to avoid it in the fridge of the society because it will lead to ozone destruction. Holophalogen. Um, yes, this family. So it leads to ozone destruction of ozone over Antarctica. How are we able to explain it? So this is the same catalytic cycle. So production equal losses leads to ozone for destruction, and we see the negative correlation. The more the CLO concentration increasing, the more the ozone concentration is decreasing. Destruction of ozone is effectively achieved by this chlorine. So there are the two processes that we just explained. Those are two catalytic cycles that lead to the ozone destruction are represented right here. We see that the N2O that is upward transformed that will be photodissociated, leading to NO, and the NO catalytic cycle can begin, forming NO2. NO2 that will react with H nu, producing NO again, and this produces the destruction of ozone. However, um, if this catalytic cycle can be stopped, reacting with OH leading to HNO3, which is a reservoir that can be reactivated. If the reservoir is not reactivated, this we have a downward transfer. This is the acid rains. The second process we have seen, the second catalytic cycle, is the one of the halogen. So we're explaining the relationship between those two catalytic cycles. They are not independent, absolutely not, and they both destruct ozone. So they both contribute to ozone destruction. With the as explained before, you got the NO, you got the HO, you got several other, you got the Cl, the halogen that will contribute to ozone destruction. So it will take time to the species to access to the upper level of the atmosphere. 5 to 10 years to access the stratosphere. Um, so the time scale vertical transport is proportional to delta z to the square divided by 2kz. Why is it so difficult to? Why is it proportional to z square? Because the convection is less and less efficient. So that's why it is more and more difficult to access the high level in the atmosphere. You got 1 and 2 years in order to drop through the tropopause due to the effect of the gravity. All right, we already included NOx. We introduced CLOX. Now we have to include two HOX family. HOX that have effect in the mesosphere. Atmospheric photochemistry role of hydrogenated constituents. Okay, origins come from natural parent molecule like H2O, methane, and the composition of the wood. Okay, so it is very natural process. So yeah, you guys, you have water that is abundant in the atmosphere that will be photodissociated, leading to OH plus H. You got this water that will react with atomic oxygen, giving 2H now. So this is the process of production of OH. Um, methane will be released in the atmosphere through those natural processes that we explained before. The same of hydrogen, they will react both with atomic oxygen available there, leading to hydroxide production. Those OH and H coefficient will react with ozone, destroying it. Um, I think it's more or less correct. Um, so three processes of destruction of ozone. OH will react with O in order to produce H. H will be able to destroy ozone again, production of the atomic oxygen, molecular oxygen that will be photodissociated, liberating more atomic oxygen, for example. HO2 will react with atomic oxygen remaining and leading to OH formation again, releasing some energy. Funny. We got a partitioning of HOX, so we got H that will be partitioned in HO2, liberating some. This is electricity, electron volt. It means that to lead to ionosphere construction. We got fast reaction activated by 4 catalytic cycle. O plus OH liberating O2. This H will react with the molecular oxygen available and the third body using a third body recombination liberating HO2. HO2 will react with atomic oxygen producing OH. Okay. This OH, there are two choices. They can react with ozone, destroying ozone, liberating HO2. HO2 they react with atomic oxygen, liberating OH. Okay. So at the end, you have this destruction of ozone process resulting. So this OH can react with ozone with atomic oxygen, liberating some molecular oxygen plus H, and this is a process of destruction of ozone again. So, and OH release it can react with ozone, as explained in HO2. It can react with ozone itself. So this is a very efficient process of ozone destruction. The relative importance of the cycles depends on the altitude, and as we say, the presence of OH is HO is majority in the mesosphere. So this is where those processes are very efficient. Production of OH. Okay. Because it needs a lot of atomic oxygen which is available at higher altitude. Um, we see that here we destroy ozone. And overall, the process will lead to the destruction of the odd family, which means the atomic oxygen too. Okay, so this is interesting because we have seen in the previous slides. I don't know if we can go back here. Especially, I think about this one. We are coming back to it. So about the atomic oxygen, where is it? Atomic oxygen. Pum, 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 pum. I do not see it here, so it's not plotted, unfortunately. You see ozone destruction. Concerning the atomic oxygen, is still alright. Yep. So destruction of old family, however, the atomic oxygen should still be a lot emitted due to photodissociation. We don't see any trend explaining that atomic oxygen destruction. So we have destruction of old family, as explained on the slide. However, it's mainly due to ozone destruction. Yep. So there are this slide is very important. So on the upper part you have the reservoir that can be activated through different manner, but they are mainly activated during the sun due to sunlight, H nu, etc. So we'll go layer by layer explaining it. So that's what we did. The atmospheric reservoir of stable compounds that are deactivated that can be activated through different processes. So if we focus, for example, I don't know, on NO3 can be activated using H nu. They are mainly activated due to sun activity. That's mainly the main way of activation of those reservoirs. On the very lower part of this graph, you have the source of active compounds. Okay, because active compounds are very important because you cannot have reservoir if you don't have active compounds at the beginning. So the releasing of those compounds are the main are the unique source of destruction of ozone. you got some different kind of origin, natural or anthropogenic. Anthropogenic mean due to human activity. I think mainly about the Cl, the chlorine, the halogen part. Here, it's mainly due to the industry. Okay. All right. The releasing of CH, where is CH? It is due to the wood, as explained before. So this is natural. Uh, Interestingly, we have those catalytic cycle because we retrieve the initial element that we had. For example, the NO, we go back and we have the NO again after the destruction of the ozone. So those cycles are interrelated, through. With it here, as explained in the troposphere, the link between the troposphere and the mesosphere, we have an intercoupling between this cycle and the other one. So, um, where is the coupling right here? hmm You see that NO is used in this cycle and this cycle also. So they are interrelated, and you see that the CLO is using in this cycle and this cycle, so they are interrelated together. All right. I don't see the direct link right here. Uh, this is the OH cycle of destruction of ozone, and that use we use OH here, but OH here also. Um, yep. So, so we put the focus on the CLNO3, which is a reservoir that can be reactivated during the sun activity or during the spring, as explained before. No, the spring is for the N2O5. The CLNO3 can be reactivated due to solar activity, leading to NO2 formation and CLO that can contribute to both cycles, as explained. Um, However, this NO2 can be retransformed into a reservoir with a third body recombination. It is possible. It is the same for CLO that can through a third body recombination too, leading to the formation of reservoir again. This reservoir can be activated. This reservoir can be activated due to atomic oxygen, leading to the formation of another reservoir, possibly, or yes, it can lead to the formation of CLO destroying the ozone due to the catalytic cycle. Um, so we have seen the anthropogenic sources and the natural sources of those halogen content, those halogen species, so CLO and Cl, are liberated in the atmosphere. Um, Thanks to a chemical reaction. I don't know what is this compound right here. However, I think it's atomic oxygen, and here we can have the sun is activating also. Is photodissociate those elements, leading to useful mm, elements for the catalytic cycle. So we switch it to totally different topics. Here, the solar wind. Talking about the solar wind, there is a slow, fast, or transient solar wind. The most dangerous one being the coronal mass ejection, leading to plasmoid um, ejection with uh, with a front of uh, of some particles, charged particles that will perturb the magnetosphere of the Earth. So coronal mass ejection are just solar flares with incredible amount of energy, leading to a reconnection of the magnetic field, leading to a redistribution of the magnetic energy into kinetical one, pushing the plasma away from the sun, beating the gravity of the sun. Um, that can lead to interplanetary solar wind affecting the Earth's magnetosphere. However, we're talking about the streamer here, how the solar wind is generated. So the streamer is forming at the boundary between open field and closed field. You can have closed field where here of magnetic field between two sunspots, for example, and you can have open fields that link the magnetic field of the Earth and the Sun. And in between them, you can have this streamer. That is a kind of I would say bottleneck, allowing the particles of the sun to to be accelerated, and leading to a so-called streamer, a slow solar wind. So this is the first way possible in order to have a solar wind. So here it's a visualization of this process. You see those connected magnetic field line, and you can see the open magnetic field line right here, and in between you have the streamers. Okay, the frozen approximation is very useful and very helpful in the explanation of the magnetic field of the sun. We have seen that the plasma moving drives absolutely the magnetic field line of the sun, and especially because uh, the sun surface is moves in a very different way. In an equator, we have a very fast moving gases and plasma, which which will just we have a critical gradient um, of velocity, like we have a cycle of uh, like the particles on the equator do a complete circle in 27 days, while we have 35 days, I think, for the one of the poles. So we have these big gradients of velocity that will distort the plasma, distorting the magnetic field with it. Um, so it is important. So we got the particle spiral. Why is it interesting? Because sometimes you have sunspots, in particular, are ejected towards the chromosphere in the corona, and when you eject a particle while the sun continue to turn on itself, um, you can go. So you will have a rotation of it, and you will see the particle initially ejected at another point here. And if you draw the trajectory of the particle, you will have this particle spiral. So this particle spiral critically depends on the ejection velocity of this particle. If the ejection velocity is very large, which means we will have a particle spiral that is less pronounced, and then a magnetic field line which is less banded. So this is important for the rest of the explanations. So this is a visualization. Here you have the sun. Uh, so where is the you have the core of the sun, you have the surface of it, and you got the magnetic field line, the positive one and the negative one. You have the same number in order to respect the divergence of the magnetic field, which is needs to be equal to zero. You can see that inside of uh, the magnetic field dominates the plasma flow and undergoes significant non-radial expansion. So we see there's a strange behavior here inside the sun. I don't know. Yeah, this is the sun. This is next to the sun. You got this strange behavior that we don't know. However, the particle spiral are very visible outside of the sun. So in the heliosphere, we have uh, this particle spiral. In the source surface, we have something very radial. Here, we have something less radial, and we see the particle spirals that are very more pronounced. Um, all right. Uh, so very next to the sun, you got the supraradial expansion, where we have something, we have stuff very much was very more complicated. Um, so we can read here the magnetic field dominates the plasma flow under the goes significant non-radial expansion with height. As the source surface typically taken to be a few solar radii, the pressure-driven expansion of the solar wind dominates, and both the field and flow becomes purely radial. So radial at the beginning, the particle spiral pronouncing as we are going further away from the sun. So as I said, depending on the solar wind speed, so we see that the speed is decreasing here, so the particle spiral is more pronounced. However, this is exactly what we say here. When the particle spiral is less pronounced, less banded, the magnetic field is less banded when the speed is very large. Um, we can average the interplanetary magnetic field strength and direction. So we have some value right here. So the Earth one is we have a theta angle approximately of 45 degrees and a strength of 7 nanotesla compared to one of Mercury. So we see that the magnetic field is very has a very large strength. So Uh, the larger the magnetic field, the lower will be uh, this angle characterizing the bending of the spiral. So we can correlating interacting regions that will it is generated when you have a slow particle ejection on the here on a part of the sun, and you got a slow particle ejections here too. So you got two particle spirals that are well banded. However, in between them, you got fast ejection leading to a radial magnetic field. So and the particles that are ejected following the magnetic field lines are compressed together, and it can lead to shock, as explained before, and it can remain and continue to rotate with the sun, as we will see in the little slide. So this is an illustration of the CIR, the correlating interaction region. So we see that when it is for the, inside this region, as we explained it, the magnetic field and the plasma temperature, the solar wind, the density, magnetic field, etc., is very large. Um, so we are following it from here to here, and this is characterized by, as explained, high temperature, high solar wind speed, high density, etc. So we represented it here. We got this normalized solar wind number density, and the CRR is very visible. It can lead to interplanetary magnetic field phenomena. So what is represented here is the explanation of the coronal mass ejection and the solar flares. So initially you got two sunspots and the magnetic fields that are connected between them. So um, so if you got more and more particles that are ejected, it will lead to a more radial flux. So this is what is happening here. The magnetic field is stronger, leading to a particle spiral that is less banded. So as we increasing it. This is due to large solar activity of the sun, and at some point, it is so large that the magnetic field here can reconnect, and this reconnection will lead to a redistribution of the magnetic energy that is very large, as explained, and this reconnection will lead uh, to a redistribution of the magnetic energy into kinetical energy, and will push the plasma, as explained before. The magnetic field and the plasma are very linked. This is the plasma that push those magnetic field lines that are opposite, and this will lead to a very huge liberation amount of energy, eventually leading to a coronal mass ejection when for the strongest events. This is a 3D representation of this coronal mass ejection, as explained. During the reconnection, individual particles accelerate to very high speed. Some of them accelerated downward into the lower solar atmosphere, and so it does not impact the interplanetary magnetic field. Okay, so as we can see right here, even if you cannot see it very well, fortunately for us, not every solar flares lead to coronal mass ejection, because there are those magnetic field lines that tends to keep those plasmoids next to the sun in order to not being liberated. So this is the sun doesn't want naturally to um, liberate those high energetic this high energetic plasma. Yep. So it can lead for the strong events to coronal mass ejections that are close of plasma and magnetic fields that have diverse effects on Earth's magnetic geomagnetic field. Mm. The two phases of the flares I explained it before. We got an impulsive phase, magnetic recognition in diffused region. Acceleration gives rise to supersonic electrons, so they are very charged particles, very energetic one. Hard X-ray developed where accelerated above the diffusion region, magnetic field and matter are released into interplanetary space as a plasmoid called the CME. So this is a representation of what's happening right here, where you have the reconnection and the release of those X-ray sources. So the second phase is the gradual phase for the radiative cooling of the previously heated gases, soft X-ray in the corona. long duration even, in order to calm down and go back to the classical situation of the sun with a magnetic field, which will be dampened right here. This is another representation of the coronal mass ejection. You got two steps. The magnetic reconnection is occurring at 1, 2, and 3 are region of particle acceleration above and below the reconnection region when you got extreme release of energy leading to shock. CME. The CME, it's a supersonic supersonic that have a supersonic front leading to shock. So it is not something soft, coronal mass ejection. Not all CMEs leave the chromosphere, only a small fraction may reach the Earth because the magnetic field of the sun here tends to keep this CME next to the sun. So you have both the magnetic field of the sun that will tends to keep to the CME next, and the gravity that is acting because the huge amount of mass that you have here and a very high temperature. So you have a gradient of magnetic field that will allow for confinement. So the CME are equal to the flux rope here. We talk about you have a lot of particles that are contained in this CME as showed here in yellow. So when those particles are released to escape, uh, are released, it can be very harmful for us on the Earth. Uh, However, most of the time, like you got an additional field that's emerging in order to protect and don't let those CME go into interplanetary space. The ejecta are not constrained to move along the particle spiral and follow a front here of here you got the plasma with the charged particles that will form what we call a supersonic solar wind that will perturb the Earth's magnetosphere. And here you got the trapped particles that were not allowed to escape. It as we said, this is long duration event, so it will stay like this a lot of times. So this is more or less yes, this is solar energetic particles that are released with that CME. Yep. All right. So the CME shocks with the particles associated to it follow the are going into the interplanetary space. Here, it looks like it follows the particle spiral, but they say that it does not follow the particle spiral. What is Now we'll talk about the content of the particles that compose this shock blow. Um, this is mainly proton, high energetic proton that contain it. However, for the solar energetic protons, when uh, this is for the CME, when you have a very large uh, this is protons that contain it, and this is very more energetic than the classical solar event particles, which are just electrons of between zero point 0.2 and 2 mega electron volt. This is the comparison of the CME composition. So you see, this is way larger. All right. I think it is. Oh, is it electrons that are released right here, or proton? This is circle. So this is proton with mega electron volt. So it is very high energetic particles that are released. All right. Can continue. So this is another representation of the coronal mass ejection, interplanetary shock. Um, So you can see here the magnetic field lines that are not connected to the sun, that are linked to the Earth, to the open magnetic field line that will take some. They can take some particles with it. So you got the interplanetary shock with solar energetic particles, solar energetic protons mainly, as seen here. This is a gradual proton event. Um, the counter streaming electrons remain attached to the sun. This interplanetary shock are contained with high energetic protons. All right. So we can talk about the Earth right now, the geomagnetic potential of the Earth, produced by a magnetic dipole at point P. So we assume that the Earth is a dipole. It is more or less correct. It's not a perfect dipole as you can expect. However, the dipole approximation at the beginning can be interesting. So the potential of a dipole is something well known in electromagnetism. In magnetism, sorry. So it got potential in spherical coordinate can be rewritten like that, and induced magnetic field B is not like that. It has a radial and tangent and transverse components. You can imagine that next to the equator, it will be a transverse component, while in the pole it is more something that is radial. This is exactly what is explained in the next slide, I think. So at the pole, you get a transverse part which is equal to zero, while at the it is something that is more radial. At the equator, you only have a transverse component. So this is just mathematics, classical mathematics, nothing more complicated. The sun is here, and it will distort the magnetic field. As you can see, it is not a dipole classical magnetic field. As we see right here, we see that the dipole of the Earth is tilted a bit. Then, if we are close to the Earth, we have something that looks like a dipole. However, the more we dezoom and we look at a higher scale, we see that the sun has a big effect on the Earth's magnetic field. So we got some properties about the dipoles with the rotational of the induced magnetic field is equal to zero. If it is not the case, if the magnetic field is not the one of a dipole, which is the case of the Earth, we have some current that is generated. We will see that we have plenty of current. We have the ring current, we have a chromosphere current, etc. The magneto current, etc. A lot of currents that are induced. The divergence of the magnetic field is equal to zero, and the curl of B is equal to the current generated if we are not in the case of a dipole. This right-hand term, right-hand side, is different from zero. In space where there are no discontinuity surface and no electric current, it can be assumed that B can be derived from a magnetic field potential. So we remain in the assumption of a dipole right here, and the solution for this magnetic field are provided by the harmonic function. So the spherical harmonic analysis generates that the potential, the magnetic potential of the Earth is given by this formula that depends on the order, etc. The more the more you introduce term, yes, this. So we have to solve the Laplacian function in order to find the potential of the Earth. That's what we are looking for. And um, so we have an analytical solution of this equation, which is this potential given by the spherical harmonic analysis. So more you introduce term in that term, it will lead to a more precise potential field of the Earth. So where here you got the Legendre polynomial of degree n ordered m. All right. So here we can see that in function of the order n, you got the energy density. You have the energy. You have the importance of each term of this sum. This is that the higher the order, the less the energy density it will introduce. You see that even if you choose n equal to 3, for example, you have already a contribution of the third terms that will be something 100 times lower than the first contribution. So if you want to be very accurate, you add more term in that term, and it will be okay. So this is mathematical, and physically, this is all right. So we're talking about the solution of the potential of the Earth when when we try to solve this Laplace equation in the spherical coordinate. When you assume that the curve is different from zero right now. Uh, Derived from magnetic potential. Yes, we assume that the curve B is equal to zero and B is minus the gradient of the potential. So we are looking for this potential of the Earth, and and we know that the solution can be found analytically by adding by the spherical harmonic analysis, and the more accurate will be the solution when you include the more term in it. So the accuracy of the solution will depend on the number of terms you add. You see that when you add one, two, three terms, you have already um, uh, a very good approximation, because the fourth one here is you have three orders of magnitude between the number four term and the number one term. So this is an internal field, core field, where here you got the crystal field, or very negligible, and here the noise. This is a very mathematical solution. So how can we imagine it physically? It's for the number one, we assume it is a dipole. When we include a second order, this is a quadrupole, and etc. etc. When you go to n equal to 4, it begins a bit difficult to imagine it. So this is just mathematical convenience. This is not a physical expression of the magnetic field, because magnetic poles do not exist in reality. It's a convenient technique for describing the field mathematically. So for n equal to 1, we can find the north pole and the south pole. We see that the south magnetic poles is in reality the north pole geographically. So um, yes, the geometric pole was tilted by 10 degrees, so it's not completely direct like this. So about the secular variation, when you see a variation in the magnetic field uh, that is higher than 5 years, that lasts more than 5 years, it is categorized as secular variation. About the magnetohydrodynamics, how what is happening in the core of the Earth, the fluid moving. Yeah, as you know that the core of the Earth is constituted of fluid. How does the fluid have impact on the magnetic field on the Earth of the Earth? So you got the variation of the magnetic field of the Earth. It is linked to this term, which is the diffusion term, and this one, which is the advection term, which depends on the velocity of the fluid inside the Earth. So you got the magnetic diffusivity 1 over sigma mu, and you got this LV over nu m, which we call the magnetic Reynolds number. If the magnetic Reynolds number is large, diffusion is relatively unimportant on the length scale. Fixed lines, magnetic fields are then advected with the fluid flow. This is the fluid flow that dominates. If RM flow is lower than 1, advection is relatively unimportant, and the magnetic field tends to rely to a diffusive state determined by the boundary condition rather than the flow. Uh, so we see that the fluid moving inside the magnetic field can have impact on the variation of it. So this is a representation of the moving fluid that have impact on the magnetic field lines, as you see inside the Earth. So, yep, the magnetic flux line escape from the core at high latitude, where helical flow reaches the core limit. So generally, it looks like a dipole. So we switch to another stuff right now. It's the shape of a magnetosphere. Magnetosphere is what it protects Earth. This is the magnetosphere is emitted by the magnetopause. Magnetopause is where we have an equilibrium between the solar wind, the magnetic field lines coming from the sun, and the geomagnetic field of the Earth. So inside the magnetosphere, so the charged particles follow the magnetic field lines of the Earth. So this is the geomagnetic field that dominate. So it is this is the shape of the magnetosphere in blue right here. Um, So we see that the solar wind is coming from the left, completely distorting the magnetosphere shape, so it doesn't look like a dipole anymore, very far away from it. So you have solar wind with charged particles that form a bow shock that will those energetic protons, especially that will come and coming in front of the geomagnetic field lines, and you got the magnetopause, and magnetosheet will take into account the fact that the geomagnetic field is protecting the Earth, completely decreasing the decelerate the energetic protons that comes from the solar wind. So magnetosheet is characterized by the deceleration of the incoming solar particles. So you have a different region here. You got the south lobe, the north lobe, and you got the plasma sheet in that form a very long tail right here. That the longer the length right here is 1,000 of times the radius of the Earth. Right here we got something that fluctuates. The magnetopause fluctuates between 6 radius to 12 radius of the Earth. So approximately more or less like this. The solar wind is incoming, completely distorting the magnetosphere as explained. So uh, so right here you get the magneto sheet boundary, the magnetopause, and you got the geometric field lines that are distorted here by the effect of the solar wind. And you got some, as we are getting far away from the shape of a dipole, we have what we call we have the rotational of the magnetic field, which is different from zero, which is that we have plenty of currents that will compensate, that will be induced. You got the chase tail current, the field aligned with the ring current, where some particles are trapped. So the particles uh, will be affected by those ring currents that will produce some aurora, etc. So trapped particles that form also the Van Allen belts. So we'll talk about it later on. So plenty of current are generated due to the fact that we are getting far away from the shape of a dipole. So there are the open magnetic field lines of the Earth. In reality, they are not open. They reconnect very far away, where we have a magnetic reconnection exactly at the same that happened on the sun, liberating some high energy, pushing the plasma in the direction of the Earth or not. Um, so as explained here, the curl of the magnetic field is different from zero. Plenty of currents are generated. So got Chapman, Ferraro current, cross-tail current, etc. This is very difficult physics that happened right here. The ring current, well-known one, that is the that will induce some aurora. Yes, as you can see here, some particles are allowed to enter the low atmosphere. So 1,000 of times the radius of the Earth in the tail, you got the magnetic reconnection of the magnetic field lines of the Earth, exactly as explained. Due to the pressure of the plasma, we have a reconnection liberating a lot of energy, pushing the plasma in that direction and that direction. So the reconnection is appearing. The solar wind and the solar magnetic field lines just reconnect after passing the Earth. The Earth is like a perturbation for the solar wind magnetic lines. So here you can have a reconnection also between the magnetic field lines of the Sun and the one of the Earth at the magnetopause. So okay. So this is a representation of the reconnection between the magnetic field line of the Sun. Um, and This is a region where you can see here very dense. We have a large amount of particles because the solar wind have energetic protons with it. We see that the magnetosphere does its job and protects the Earth from it. This is when the magnetic field line are in that direction, the one opposite to the Earth one, allowing for magnetic reconnection. When it is not the case, when the magnetic field lines of the sun are in the are in the same direction as the one for the Earth, we have error connections that appear later on at the pole, allowing for more. Allowing for more. There will be error connection here and here, and it changes the shape of the distortion of the magnetic field line. So about the magnetosphere, we have plenty different regions. The closest one is the plasma sphere that contain particles with low energy, fortunately for us, that drifts up from the ionosphere, forming a reservoir. Okay. After that, you got the ring current, population of medium energy. As explained before, it's due to the fact that the Earth's magnetic field is different from the dipole one, so it generates plenty different currents. You got the electron radiation belt, particles that are trapped in two regions. These particles move along the field line towards the pole until they are reflected back, creating the bouncing movements. Yeah, bouncing movements that we will be able to explain later on. Um, if if uh, if the bouncing movement is sorry, we'll have the definition of the loss cone. We talked about it, and if the angle is low enough and it allow the particles to travel and not be bouncing, it can enter the Earth sometimes. So radiation belts, electron one and proton one. Yes, the ring current is induced because of the tilt of the protons and the electrons. They are tilted in opposite direction, creating that net current, call it the ring current. So another representation right here of what we talked about, the Van Allen radiation belt, two spatial region, the inner belt and the outer belt, where we don't want the satellite to travel inside in order to not have not being electronically perturbated. So the ring current is due to the fact that the drift of electrons and protons are in opposite direction, so it creates a net current. So the mirror point, we have trajectory of trapped particles, and they do like this. They follow this trajectory. Okay, where here the parallel velocity to the field of the magnetic field is large, and here you got this parallel velocity that is slowing down until reaching this mirror point, where we have force in opposite direction to the magnetic field that that counteract exactly the value of it, and they will follow this shape, creating those bells. This is exactly how it looks like. So it explains. So the gradients of magnetic field is inducing this mirror bouncing that protect the Earth at the end. Because if there were no, if there was not this phenomenon, the particles would be all allowed to fall here on the pole. So this is a force induced by the gradient of the magnetic field. Why do we need to care about those particles? Because we have satellites, and we do not want them to be in a zone where we have a high particles activity, because they will hurt our satellite electronics, especially. So we do not want it. So a deeper look at the plasma mantle. So origin of enhanced magnetic field B, acting as partial barrier to the shock at solar wind. So yeah, the particles of the solar wind are very decelerated, and we have a large magnetic field needed in order to contract it. Some solar wind particles become trapped within the first few kilometers. This is what it forms a plasma mantle. Those particles are actually stuck right here. The lobes of magnetic field within the plasma mantle. Tenuous cold plasma from the evaporation of the ionosphere. B field is opposite in north and south lobes. Uh, it is relatively a neutral region right here. So we have reconnection can happen at the boundary right here. The magnetic field lines are in opposite direction. We got the plasmoids. Plasmoids are induced by um, the reconnection of the magnetic field line pushing towards the interplanetary space, this plasma burst of plasma. Mhm. This boundary of the plasma sheet is the source of most auroral events because they are allowed to. This is where the gradient of magnetic field is the less sharp, allowing for the mirror points. Uh, this we have a large loss cone right here because the gradient of magnetic fields is not that large, allowing for the particles to enter. Uh, to have to enter and creating to the auroral events. So auroral are just plasma linkage into the atmosphere. So they are able to enter inside. Um, so they beat the magnetosphere. The magnetofield, sorry. This is typical value and what's happening in those regions. So yes, so just have to read what is happening right here. In the plasma field, we have cold plasma terrestrial origin in the plasma sphere. Uh, yep. Plasma sheet thickness of 4 to 6 times the radius of the Earth forms into the ring current from the Earth. This is plasma sheet. Where is it? Okay. Uh-huh. The plasma sheet boundary layer. This is the we have auroral zone. Okay. Lowest density is found in the magnetospheric cavity. Lobe, okay. Nothing very happened in that region. Entry layer into the magnetosphere, which is the mantle. So the magnetopause here will strongly vary. It is very the fight between the solar wind and the magnetosphere, the geomagnetic field. So we can compare the energy of the solar wind and the magnetosphere. We have three main sources of energy. However, we will neglect plenty of them. For the solar wind, we'll neglect what will we neglect? The kinetic energy? Absolutely not. The thermal one will be neglected compared to the kinetical one, and the electromagnetic one we will keep it. However, for the Earth, we'll just keep the electromagnetic one because the kinetic is not useful in the thermal too. So when we do this equilibrium, we are able to approximate the region when we have equality of this energy, the solar wind and the magnetosphere. This is where we have the magnetopause, so it varies a lot. So it was a dynamic slide showing the evolution of the magnetopause depending on the solar activity. When the solar activity is large, the magnetosphere doing its job. However, the particles are able to enter more closer to the Earth until reaching sometimes the geostationary Earth orbit, perturbating satellites. Uh, so after that, we try to explain. Am I recording? Yes. No. I don't know. Yes. Yes. So now we'll try to explain the motion of the particles under the effect of the magnetic field. So the electric field and the magnetic fields are assumed to be prescribed and not affected by the charged particles. All right. So first case, there is this one. We neglect any electric fields. So Lorentz force affect the motion, the variation of velocity of the particles. So we assume that the magnetic field is in the z direction for sake of simplification for the moment. So this is a curl product, so that we got, and we project it into the three direction. So it is interesting that we got right here. We got those are two the variation of velocity in the y and the x direction. This is quite a simple harmonic oscillator at the cyclotron frequency, which we define the positive value. We don't have any motion in z direction in the direction of the what? Of the magnetic field. So it remains at the same place. However, it just turned. So, and we can describe the frequency of the cyclotron frequency. Simple as that. So we can find Vx and Vy like this. We may choose the phase and. So speed in the plane perpendicular to B, uh, Vx. Uh, right. However, we don't move in the direction of B. We just turn. Simple as that. Vx, Vy. After integration, we can find the Larmor radius. Uh, the radius depends on the mass of the particles. It depends on its charge and the magnetic field. And V perpendicular. V perpendicular is described as. What is the definition of V perpendicular? All right. I don't know where we defined MV perpendicular. Yes. Vx assumed to be the perpendicular. No matters. The mass and the charge is very important. So what we will have, so they are just uh, they are just making cycle. The electron has a very small Larmor cycle because the mass is very slower and the charge is lower. However, the this ratio is very lower than the one of the protons. They move in opposite direction because uh, they move in the electrons move like this, and the positive ions move like that. I don't know because we take the absolute value, so it means that V perpendicular depends on the particle charge. Yes, the sign of Q is induced like this. So they rotate but in opposite direction. When you have an electric field that is induced, and it is the case because we know that the uh, we have seen it in electromagnetic cores that we have the Poynting vector which links the B and the electric field. We may choose E to lie in the EY plane, so the Lens force can be rewritten like that, the Lorentz force. So now the main difference is that we have a VZ direction, so it means that it will just continue to turn following the same law, um, except that will have another contribution in of EX right here. And however, the main difference is that we will just continue to move in the z direction. And we see that the velocity through d is increasing with time. Okay? And the variation of the velocity through x and y, so they are making us not exactly a circle right now, as you can see. If we have constant v, we can do the calculation and find vx and vy in vx direction. So it will move in z first. That is very important. Uh, uh, so they are not showing it right here. We have the Larmor motion is the same as for e equal to 0, but there is a superimposed drift in the y direction. However, I see that we have yes, we assumed that we have ease. Um, okay, we assumed so is equal to 0 too, which means that we don't have motion in the z direction. So because B and E is perpendicular, E is in the direction of EX, so it will induce that we will have a drift in the Y direction. So just where is the Y direction? So X is like this, Y is like that. So we have a Vy that is decreasing. So they both go downwards compared to y. We assume that easy is equal to 0 right here. If we had easy, it would have been different because we will move in the z direction at the same time. However, for the moment, we move in y direction due to the fact that e is in the x direction. All right. So we have seen that when we have an electric field in the ax direction, it induces a tilt in the y direction. Okay, so opposite to the direction of the magnetic field. We are not in the direction of the magnetic field at all. So it is interesting. In the more general case, the motion of the Whiting center corresponds to the MDVDD. It gives the circular motion. Mhm. Uh, so perpendicular electric field and magnetic field is completely logical. Um, so we have an electric field that drifts off the Whiting center. Okay, in a direction which is not the one parallel to the magnetic field, but the perpendicular direction. So what do we see right here? Up. Wow. So now the most important tilt is the tilt induced by the gradient of the magnetic field. So the magnetic field is increasing towards it's increasing. Okay. However, here we see that the magnetic field is increasing in the direction perpendicular to it. However, what is happening in reality is that we have an increased magnetic field in the parallel direction. So this is just a representation that we have right here. So the magnetic field is increasing in perpendicular direction, and we have the Larmor radius, which is changing, which will induce an opposite drift direction for plus and minus charge, which leads to the net current, which is in reality the this is exactly the generation of the ring current, the origin of it. So the gradient of magnetic field in perpendicular direction. We also see later on that the gradient of the magnetic field in the parallel direction will induce that not a net current, but it will induce um, the mirroring points, the mirror points. So the variation of the magnetic field perpendicular to it induce a ring current. Interesting. All right. Starting um, starting from the solution for a uniform magnetic field, we consider the effect of perturbation associated with gradient V in the y direction. The perturbation is evaluated with a Taylor series expansion, so we can quantify it. This is the force induced in the y direction when we have a gradient of magnetic field in the y direction itself. So so this is exactly what's happening right here. So when we have a gradient of magnetic field in the perpendicular direction, it will induce that the electron will move in the left direction while uh, the protons will move in the right part, inducing a net current. All right. Uh, all right. They drift in opposite direction. The Guilding center drift velocity can be calculated following this formula, and we see that the drift velocity is proportional to the gradient of the magnetic field in the y direction. All right. We see that this velocity induced depends on the sign. This is why we have ions and electrons that go in opposite directions, and this creates this current density. And this is exactly how we got the ring current. When we have a gradient of magnetic field, knowing the direction of this magnetic field itself, this is a bit different. So that's exactly what's happening here. So we have a magnetic field that is proportional to 1 over r cube right here. So the closest we are to the Earth, the harder the magnetic field is. So we have so the magnetic field gradient will have an impact in creating what we call the magnetic mirror point, because this gradient will induce a force in opposite direction to the magnetic field, and it will just slow down those particles. So here we have the angle alpha that explain us. So the higher alpha, the higher V perpendicular will be, and the lower alpha, the higher V parallel will be. You see that at the equator alpha is equal to 0, and at the pole alpha is equal to 90 degrees. All right. Non-uniform magnetic field that displays an intensity gradient in the direction of the field lines. So we see that we have a lower field strength and a higher field strength here. So we have a magnetic field gradients, and we have a force Fz in an opposite direction of the magnetic field Bz. The force perpendicular to the guiding center field line Fr is responsible for the gyration Fr. Okay. The force parallel to the guiding circle is produced at an acceleration direction of the diverging field line, or what we call a deceleration. Using the cylindrical coordinates, we can describe. We, we know that the divergence of this magnetic field need to be equal to 0, and the variation of this magnetic field with respect to z doesn't vary a lot with r. It mainly vary in the with the z in the z direction. So Fz induced, so the force that will slow down the particles is proportional to the variation of intensity of this magnetic field, arranging over one gyration of a particle whose guiding center lies on the z-axis, and v0 is constant during a gyration depending on the sign of q. V0 v theta is minus or plus v perpendicular. So the average force can be found out with some mathematical tricks. So here we replace the V perpendicular by its value. No, V perpendicular stay here. The Larmor radius is replaced by its definition. And what did we simplify? Here omega c replaced by its definition too. And we see that the average force in the z direction is proportional to the magnetic moment mu, which is defined as 1/2 mv perpendicular square divided by b, which is always the magnetic moment of the gyrating particle. We know that I forgot the discussion about the magnetic moment, but it remains there. And so the variation of the magnetic field in that direction will induce a force that will stop it. And we see the minus signs, which is the very important, very most important things that we have here. As the particle moves into the regions of stronger or weaker B, its Larmor radius changes, but mu remains invariant with the with B, so it stays always there. So F parallel is this is the definition what we got right here, and we use a curvilining variable here in order to be as general as possible, and we have the here this is Newton that we just applied, and if we play a little bit with it, we can have the energetic expression. So we got that the variation of the magnetic moment with respect to time is equal to 0. And the magnetic moment, we know it. It is definition, we have it here. So we replace it, and v perpendicular is equal to v sine alpha. So what is interesting here is that the ratio between sine square alpha over b is equal to a constant. So with it, we can find the at the mirror point, we got alpha, which is equal to 90 degrees, because we don't have any V parallel anymore. So we sine square alpha divided by b is equal to a constant. If we increase b, we have to reduce the alpha angle. hmm So let's see what's happening right here. Sine square alpha over b is equal to a constant, which means that if the alpha angle increase, the magnetic field has to decrease. Uh, I don't know. We can find the yes, it allows us to find the magnetic field where the particle is mirrored. That is the purpose of it. Yes. So it's we are able to know where exactly the particle will be mirrored. So that's interesting. And there you got the loss cone. If the alpha angle is too small, is in this loss cone, the particle is able to not be mirrored and access the Earth's atmosphere and leading to the aurora events. So that's exactly what we need to remember from it. So, um, yep. All right. There we got the trapped population of charged particles that bounce like this, like them, and when the alpha angle is low, is somewhere in it. V perpendicular is way larger than V parallel. No, V parallel is larger than V perpendicular, allowing the particle to pass that mirror point. So we talked about the bouncing and drift. This is both due to the gradient of the magnetic field. We got a gradient of magnetic fields in the um, with so we have two kind of gradients parallel to the magnetic field and the gradients perpendicular to the magnetic field. So we got the gradient which is in the line direction and the gradient which is perpendicular to it. The gradient perpendicular will lead to a particle will lead to the production of drift, and electrons and protons moves in the opposite direction, leading to that net current. And the gradient in the direction of those magnetic field line will uh, will induce a force in the opposite direction of this magnetic field, and that can counteract the effect of the magnetic force, and you reach here what we call a bouncing mirror. And it explains plus those regions in the magnetosphere where we have a large amount of particles. So it explains a lot of stuff. The DST index, so it is a disturbance storm time, its relation to the ring current and storm phases. So here, yes, you got ring current that is created because of the drift induced by the perpendicular gradient, and this will induce um, a ring current. A ring magnetic field that will be opposite to the one of the Earth, and this is what measures the disturbance storm time. How, as the ring current magnetic field is opposite to the one of the Earth, um, if we notice a reduction in the resultant magnetic field, it will mean that we have a large ring current affecting, uh, creating what we call a disturbance storm. Yep. So magnetic field in the center of a current ring is given by this. For the magnetic field disturbance of the Earth's surface, uh, yep, uh, Current ring of radius r is given by this. For the magnetic field disturbance at the Earth's surface, um, so this is at Earth's radius. I don't know what's happening. This is the variation induced at the Earth's surface. It is given by that. Whereas the geocentric distance and delta IRC, the disturbance inducing enhancements of the ring current intensity. So it will induce a variation of current. The intensity of a ring current at L equal 5 would need to be increased by 5 million ampere to produce a measurable magnetic field disturbance of minus 100 nanotesla. Uh, so, no matters. So variation of the magnetic field is induced by current ring magnetic field generation due to the ring current. So it brings us insight about the magnetic activity indices. The disturbance storm time index is a measure of the geomagnetic activity used to assess the severity of magnetic storms in nanosecond and based on the average value of the horizontal component of the Earth's magnetic field, measured only at four near equatorial geomagnetic observatory. So we got plenty. So we mainly do that at the Earth's equator. So whether this. All right. So this is why we do it at the equator. There was the explanation for it. Yes, wait, okay. This is because the ring current induce a transverse magnetic field, and this is way more easier than a radial one. So um, this is why we use this. The DST index. So we see here that the magnetic field is affected. We have when we have a storm, we have a reduction in nanotesla of the magnetic field. So this is this drop here. That is the effect of the storm, the effect of this ring current. A stronger ring current causes DST to decrease. All right, we got this recovery phase right after where the geomagnetic field continue to dominate. The strength of the surface magnetic field at lower latitude is inversely proportional to the then energy content of the ring current, which increases during geomagnetic storm. All right, we have a sudden commencement and then decrease sharply as the ring current intensifies. Logically, the interplanetary magnetic field turns northward again, and the ring current begins to recover. So the DST begins back to the quiet time level. So it is the end of this long journey. So it was long, very interesting course, but there are a lot of topics. I hope, inshallah, that the exam will pass well. Um, so I appreciated this course, honestly. The part of the magnetosphere is a bit hard. Um, However, in reality, there are plenty of topics that were everything was new to me. The CME was a complex topic, very new for us. Never heard about the CRR before. This is the course when I have uh, where I have maybe learned the most amount of things. The ozone production and destruction, very hard topic also. So it's very amazing to see how complex is the interaction between the sun and the earth, how complex our atmosphere is, how beautiful is it, the way the sun the atmosphere is protecting us for the harmful parts of the atmosphere, the harmful UV light, how it is beautiful the way uh, This one is beautiful, like how the way uh, the sun light in the visible is not absorbed. So it's it's quite nice. It was very interesting, honestly.